to Linear Algebra, Chapter 3, Section 3. Today's topic is the kernel and image of a linear mapping. We already saw last time concerning the kernel of a linear mapping, although we had not called it that at the time, but let's look at it and look at our definitions. Let f from V into W be a linear mapping. The kernel of f, denoted by ker f, is the set of all vectors v and v so that f of v equals the zero vector in W. In other words, the kernel of f is a subset of v that contains all the vectors in v that get mapped to the zero vector in W. Now recall that any linear mapping maps the zero vector in V to the zero vector in W. So we already know that the zero vector of V is in the kernel of F. Now look at the first example. Suppose we have a linear map L going from R3 to R, defined in the following way, where L takes an ordered triple x, y, z and maps it to the real number 3x minus 2y plus z. Now, you can easily see that if you let A be the ordered triple of the coefficients 3, negative 2, 1, then we get what we call L sub A, the linear map associated with the vector A. So the map L is nothing more than the dot product of A with any vector x in R3. So the kernel of L consists of the ordered triples x in R3, so that the dot product of A with x is 0. In other words, the kernel of this map consists of all vectors in R3 perpendicular to the vector A. Okay, now notice what you can do with that one. So the kernel of L consists of the ordered triples so that 3x minus 2y plus z equals 0. Now take that equation, solve it, say, for z. You could have solved it for x or y, but solve it for z. Z equals negative 3x plus 2y. So that tells me that x and y are independent and that z is dependent. And I'll say more about that in a little while. But at the moment, I want you to notice this. If we let W be the span of A, and then let U be the kernel of L, then U is the orthogonal complement of W. And we have that R3 is the direct sum of W and U. So that relates it back to direct sums. Now that was not in the textbook, but I wanted to add that in there. Now, in general, given L sub A from Rn to R, then the kernel of L, or L sub A, would be the set of ordered n-tuples x in Rn that are perpendicular to that vector A. Okay, let's look next at example 2. Example 2 is the projection mapping from R3 to R2. Okay, take an ordered triple and just knock off the third coordinate. Okay, so we see that the kernel of this projection mapping is going to be the ordered triples that get mapped to 0, 0. Notice I used the notation, the vertical line with the arrow to make it more clear. And so what is that kernel for that projection? Well, it's the ordered triples 0, 0, z, where z is any real number. So that turns out to be a one-dimensional subspace of R3. The one from example 1 is actually a two-dimensional subspace of R3, and we'll see that more clearly momentarily. All right, so next, let's look at our next portion. We're going to now look at a very important property of the kernel of a linear mapping, and it's this following theorem that I have written down. Theorem: let f go from v to w be a linear mapping, then the kernel of the map consists only of the zero vector of v if and only if f is injective or one-to-one. Sometimes we say the kernel is trivial if and only if f is injective or one-to-one. And this is always going to be our test to check whether or not a linear mapping is one-to-one or not. It's one-to-one if its kernel is trivial. Now the proof is very straightforward. Let's look at it. In the forward direction, first suppose the kernel of f consists only of the zero vector in v. And let v and w be vectors in v. We're trying to show that f is one-to-one, so let f of v equal f of w. So if you subtract f of w to the left side, you see that f of v minus f of w is the zero vector, equal the zero vector of w. But since f is linear, we can rewrite it as f of v minus w equal the zero vector. And so that means, of course, since the kernel is trivial, it means that v minus w is the zero vector of v. Hence, v equals w. In other words, now we've shown that f is one-to-one. In the converse direction, suppose f is injective or one-to-one, and if v is in v with f of v equal the zero vector in w, we need to show that v can only be the zero vector of v. Well, what do we know? We know that f maps the zero in v to the zero in w. So now we have f of v equal f of zero v. Hence, v equals 0v, since f is injective. And so it's an if and only if theorem. Very important. Now let's look at theorem 3.1. Now theorem 3.1 says the following. Let f be a linear mapping, and let the kernel of f be trivial. If v1 through vn are linearly independent in v, then the images vf1 to vfn are linearly independent in w. So in other words, when the kernel is trivial, which means that it's one-to-one, then the mapping preserves linearity. If a set of vectors are linear in v, their images linearly independent in V, then their images are linearly independent in W. So let's look at the proof of this statement. Okay. So we have to start out with a set of scalars, x1 through xn, with a linear combination of the FVI's equal to 0 vector in W. But since F is a linear mapping, we know that we can take those linear combinations and rewrite it as F of evaluated at the linear combination of the VI's with the XI's. Okay. But now the kernel of F is only the 0 vector in V. So that means now that our combination of XI VI's equals the 0 vector of V. But since the VI's are linearly independent, that means that all of the scalars xi must be 0 for all I 1 to n. Hence, we've proven the theorem. Okay? Next, we look at the image of a linear mapping. The image of a linear map is defined by and denoted by the symbol IMF. The image of F consists of all vectors W and W such that there exists vector V and V with F of V equal to W. So image here really is another word for what? Range. The range. We claim that the image of F is a subspace of W. Let's look at the proof. So to say that a subset is a subspace, we first take two vectors in the subset, so let W1, W2 be vectors in the image. So by definition, that means there exist vectors V1 and V2 and V, pre-images, with F of V1 equal W1 and F of V2 equal W2. Now, we know, of course, that F is a linear mapping, and so let's see what happens. 1, F of V1 plus V2 equals F of V1 plus F of V2 equals W1 plus W2. So that means that the sum of W1 and W2 is in the image of F because it has a pre-image. And then if C is a scalar, F of CV1 is C times FV1 equals CW1. Hence, CW1 is in the image of F. I didn't have to include the third one, but I just note the 0 vector of W is also in the image of F, since F maps 0 to 0. Now, the big theorem in section 3.3 is theorem 3.2. This is the big theorem, the big dimension theorem. And we're going to use this theorem throughout the remainder of the course. That's how important this one is. It's huge, tremendously huge. All right, look at theorem 3.2. Now in the textbook, for purposes of the proof, they define the dimensions by various letters like S and Q, but I didn't do that because I'm not looking at the proof of this theorem. But what does it say? It says whenever you have a linear map, L, going from V into W, then the dimension of V is equal to the sum of the dimension of the kernel of L plus the dimension of the image of L. Let's see how this would relate to our previous example. Recall example 1, where we had ordered triples going to a real number, 3x minus 2y plus z. Okay. Now, if we were to apply this dimension theorem, first note that the image of this linear mapping is all real numbers. So the dimension of the image is 1. So that means we have the following. Dimension of R3 is 3. All right, the dimension of the image is 1. Hence, the dimension of the kernel has to be 2. 2 plus 1 equals 3. And we also saw that a while ago because the kernel, which is the ordered triples, where z is dependent on both x and y, tells us that x and y are independent parameters. So that means the dimension of the kernel is 2. All right. Next, we have our next example, going back to example 2, where we looked at the projection mapping from R3 to R2. So notice the projection mapping. Okay. The projection mapping is clearly surjective, or onto R2. So the dimension of the image is 2. Hence, the dimension of the kernel would have to be 1, because the dimension of R3 is 3, and 3 equals 1 plus 2. And recall that the kernel of this projection map was the triples 0, 0, z, where z is the independent parameter. So that tells me also that it has dimension 1. Now here's a preview. Example 3, this is not in the text, this is my example. Let's take a matrix A, m by n matrix A, over the scalar field K. Consider the linear map L sub A associated with the matrix A, going from Kn to Km. Remember, it's defined as L sub A of x equals A times x for all x in Kn. Then the dimension of Kn, which is n, equals the dimension of the kernel plus the dimension of the image. Now let's call the dimension of the image by the letter r, the lowercase r. And we're going to find out later that this r stands for the rank of the matrix A. The rank of a matrix is the number of linearly independent rows or columns of the matrix. And so that would mean that the dimension of the kernel would be n minus r. Now, relating to matrices, the kernel of L sub A is the solution set or solution space of the homogeneous linear system, AX equals 0. And the image of L sub A is equal to the column space of the matrix A. Recall, the column space of A is the subspace of Km spanned by the linearly independent columns of A. And then finally, we have theorem 3.3, which we will state, and I don't intend to prove it, it's simple, but here's what it says. Let L be a linear map, V to W, and suppose the dimensions of V and W are the same. Okay? That means that V and W are actually isomorphic, almost. Let's see what is needed for this to be an isomorphism. This is what theorem 3.3 is all about. If V and W have the same dimension, then if either the kernel of L is trivial or the image of L equals all of W, then L is bijective. If either one of those are true, then L is bijective. So homework 6 is on page 63. The turn-in exercises are numbers 3 and 4. So you notice that number 3 there is finding the dimension of a subspace of R4. And number 4 is a very important problem. Look at it. Let L, V to W be a linear map. Let W be an element of W. Let V naught be an element of V, so that L of V naught is W. Show then that any solution of the equation L of X equals W has the form, or is of the type, V naught plus U, where U is an element in the kernel of L. Now it's very important, and it goes back to looking at non-homogeneous linear systems, AX equal B, and the format of their solutions. The solution to a non-homogeneous linear system is equal to a particular solution, say V naught, plus any solution to the associated homogeneous linear system. So that concludes our lecture for 3.3.